All right, looks like it's 2:55, so we might as well get started. So my goal today is roughly twofold. The first thing I want to do is address the issue that we got to at the end of by the end of class the last time, which is in these addition reactions to alkenes. It doesn't take long before you get to a situation where there's multiple possible products. And we need to have a method that we can use so that we can know which is the right answer, which is the major product. Now, depending on the reagents you choose, and you might have noticed this also in the OWL problems, if the thing that you're treating your alkene with, if the reagent you're treating the alkene with is symmetrical, then there's no issue. And the way you know, well, first of all, the way you know this is symmetrical, I think you will agree, the bromine molecule is symmetrical. It doesn't matter which way you write it, it's the same thing, right? So that's one thing. In order to go further, you need to know what symmetrical means and how to decide whether something's symmetrical or not. I think it's pretty clear. Br2 is symmetrical, Cl2 is symmetrical, H2 is symmetrical. Do you all see what I mean? So in those cases, we have no issue. And the way you know that is because the two carbons that used to be in the alkene both get the same thing attached to them in the product. In this case, two bromines, or it could be two chlorines if it were Cl2, or two hydrogens if it were H2. So there's no issue. That's the only possible product. And the way you know that, again, is it doesn't matter which of those BRs you put where first. You will get the same thing either way. Do you see what I mean? I mean, if not, you can try it. First try putting one bromine on, then try putting the other. I should say, though, I'm also presupposing, and I realize we're just starting, there's still time before the exam, this also presupposes that you know these reactions, so that you know that when you treat an alkene with Br2, you will get the dibromide with two bromines, one on each of the two carbons that used to be the alkene. Remember our step-by-step method. You turn the double bond into a single bond, and then you add a Br on each of those atoms. If you're given Br2, if you're given Cl2, then you put a Cl on each of them. Do you remember talking about that the other day? So that's what it means to know the reaction. It means, among other things, you could be given an alkene you've never seen before, but and told which of the reagents we discussed that it's reacting with, and you can figure out what the product will be. It doesn't mean memorizing the examples we did in class. That's not going to do you any good, I can virtually promise you. So my first point here is, if the reagent is symmetrical, then even if the alkene is not, and I would say this alkene is not symmetrical, the way you know that is you look at the two carbons in the double bond, and you observe one of them is a hydrogen and one of them is an ethyl group on it. They're different from one another. Those are two different things. So this alkene is not symmetrical. Again, I'm assuming you know what the word symmetrical means and how to tell whether something's symmetrical. But do you see what I mean? Does everyone see that the alkene is unsymmetrical in this case? But it doesn't matter because the other reagent is symmetrical. And in that case, there's no issues. There's only one product possible. Likewise, if we do it the other way around, oh, wait a minute, did I do this right? Is the symmetry due to the single bonds? The symmetry or lack of symmetry is due to, in other words, it doesn't have to have a single bond to be symmetrical. But you can tell that if you try to draw a mirror plane down here, you're fine. The left side and the right side are the same. That's what symmetry means, right? But if you try to do that here, you're not going to succeed. The two sides are different. And there's no other way you could turn that so that it is the same. So does that make sense at all? Is this helping you to see what I mean by symmetrical? I need to make sure everyone gets this, because otherwise I'm not going to make sense. But it's just a simple thing by inspection that you do. So the first point I'm making here is, if either the alkene or the reagent that we treat the alkene with, if either one of those two is symmetrical, there's no issue. There's only one possible product. And I think I just proved that in this case with the reagent being symmetrical, even though the alkene is unsymmetrical. Now, how can you know that this alkene is symmetrical? Because if you put a mirror plane right down the middle, then it's the same thing on either side. There's an ethyl group on one carbon and a hydrogen in the other. Hydrogen and ethyl group. That means this alkene is symmetrical, at least for the purposes of this reaction. The cis version of the alkene would also be symmetrical. Likewise, this alkene would be symmetrical if either we took away the ethyl group or added another ethyl group on the other side. Anything that you can do to make the left side the same as the right side means that you will have a symmetrical alkene. And if the alkene is symmetrical, then it doesn't matter if the other reagent is not symmetrical. Sulfuric acid certainly isn't, right? Where is the bond in sulfuric acid that's going to get broken? So you need to know that. That's part of knowing this reaction. And the bond is either one of those OH bonds. Doesn't matter which, they're the same. So indeed, sulfuric acid is a symmetrical reagent, but when you consider where the bond breakage is occurring, those two pieces are not the same as each other. That's how you know that this is acting as an unsymmetrical reagent. And the same would be true of HCl, HBr, HI, or H2O. In both cases, in all of those cases, when you look at the bond that's breaking, and as a visual aid you draw a line down that bond, you'll see the two pieces are different. That's what we mean by an unsymmetrical reagent. I'm really trying very hard to define these terms so that I'm making sense. Is this making sense so far? Everyone following? Because you need to be able to tell this in order to get this right. You need to be able to tell if the alkene's symmetrical or not, and you need to be able to tell if the other reagent is symmetrical or not. And goodness knows you're not born knowing this. Everyone, I understand that. And if I don't tell you how you can know it, you know, I don't expect you to read my mind. So my point here is, although the alkene, even though the alkene is symmetrical, so how can you tell on the Lewis structure? You can't tell just by looking at the Lewis structure. You have to know what the molecule's doing. This is chapter 3 still. This is exam material. We'll start chapter 4, I anticipate, on Friday. And this is specifically in section, let me get it for you. This is in section 3.8, and I hope to finish chapter 3 today. So, good. Right, you have to, exactly, this person, you have to look at the bond that's breaking, so you have to know that as part of the reaction. You have to know when you're treating it with bromine that it's the bromine-bromine bond that's breaking. That one's fairly easy, there's only one bond. And you have to know with sulfuric acid, it's this one. If you're using HBr, or let me do HCl since it's a little different, that it's the hydrogen-chlorine bond that's breaking. Again, that's, can the bond break between the O and the S? There might be ways to do that, at least in several steps, but not in this reaction. In this reaction, it's always either of the OH bonds that breaks, no exceptions. You can count on that. You can be confident about that. It's always going to be the OH bond. And the way you know that the OH bond is suspicious, by the way, is because in Gen Chem you learned that sulfuric acid is a strong acid. What is an acid? It's something that gives up H+. So we expect the bond to the H to break. That's not surprising if we understand that sulfuric acid is a strong acid. It means it really wants to break the bond to the H, and the only thing the H is attached to is the O. So it has to be that bond. Does that help? Does that make sense at all? I'm just trying to show you how you can narrow it down and how you can make some sense out of this. So our first point was that if the reagent that we're treating the alkene with is symmetrical, which I guess is H2Br2 and Cl2, I don't think I'm forgetting any, then even if the alkene is unsymmetrical, only one product is possible. In other words, you don't have to worry about it. There's no issue. Meanwhile, if the alkene is symmetrical, then even if the reagent is unsymmetrical, which this one is because of the bond that breaks, then only one product is possible. I put the sulfate group over here. If I'd put it over there, it's the same compound. You've just turned it around. So only one product is possible. So my point here, and this is something you will need to know for the exam, is that if you're doing an addition reaction to an alkene, we sometimes have to worry about getting multiple products. And in those cases, we need to know how to figure out which is the one we will get the most of, which is the one that we call the major product. My first point is, if either the non-alkene reagent or the alkene itself, if either of those is symmetrical, there's no issue. So as long as the alkene or the reagent is symmetrical, there's only one product. Exactly right. I couldn't have said it any better myself. That's exactly what my first point is. Now, you're going to run into cases where both are unsymmetrical. You no doubt already have an owl. So that's what we need to know how to deal with. And that's where Markovnikov's rule comes in. And I'm not even so excited that you particularly memorize or learn to spell Markovnikov. That's not really the issue. But I would like that if you see that name and the rule associated with his name, that you understand what it means. Now, I have defined Markovnikov's rule in your chapter 3 class notes. I just want to go back there and make sure that I just looked at it, so I want to make sure. It's in the class notes for section 3.8, which I've put in chat. So I've given you Markovnikov's rule, I've defined it, I've spelled it all, and I'm going to say it all here first. I'm not just going to say, you know, read the notes and get out of here. I'm going to go over it here, but I just am saying that so you don't think that if you miss what I said, you'll miss something. It's all in there in the class notes. I've defined it, I've spelled out exactly what it means, and I've given you a step-by-step method that you can use to apply Markovnikov's rules so you know what the right answer is. That's all there in the class notes for you. And we'll do some examples too. That's my first goal for today, is getting through Markovnikov's rule and doing some examples. I do have, as I said, one brief question for you guys using polling this time. Still, please do register your attendance, but I'll go over that as well. And after that, the remainder of chapter 3 is essentially a quick review of some other things from Gen Chem, just a few other things that I think are important to at least bear in mind. And I've spelled out in the class notes exactly what you have to know. I've mentioned which are the topics that are going to be important. And I've spelled all that out because I don't think I'm going to have time to cover every little detail in those last few sections. But there are going to be some that I'm going to spend a little more time on because they're a little trickier. They're generally covered in Gen Chem. In a 2-semester sequence, they'll often get to them in Gen Chem 2, some of these things. But these are standard Gen Chem issues. And although I'm presupposing knowledge of these things, I think it does us all some good, myself included, if I can go over some of these things a little bit more so that you're clearer on what sort of things you need to apply from Gen Chem, because these are things that will help you understand reactions. And that's what I'm expecting of you guys, at least at some level, that you understand the reactions we do. Yes, I know this is just a survey course, just 1 semester. You know, we're not going to go completely crazy with mechanisms. I'd kind of like to show you one example of a mechanism today. I hope we have time for that. It's not something I'm going to emphasize greatly. There won't be 1,000 questions on it in the exam, maybe 1 or 2 occasionally. But it's the reason it's good to at least go over it a little bit is having at least an inkling of what the mechanism of the reaction is. By mechanism, I mean the steps that the molecules go through to turn from the starting materials into the products. These are known for a lot of reactions. Like I said, we're not going to do much of it. I won't say none. We'll do a little, but we're not going to do very much of it. But in this case, I think I can show you that Markovnikov's rule makes a ton of sense. And if you understand the reactions at least a little bit, then you don't have to rely on memorizing sentences. Because what if a sentence gets unmemorized by the time the exam comes around? So you'll see that Markovnikov's rule, I hope, is something that makes a lot of sense. Good. So with that, let's look at an example of a reaction where we do have to care about all this. I think I just need more room. So let's take an unsymmetrical alkene. How about that one? I think you'll agree that one's unsymmetrical. This alkene carbon has 2 methyl groups on it. This alkene carbon has an H and an ethyl. So that alkene is unsymmetrical. And let's go ahead and treat that with an unsymmetrical reagent, like, I don't know, how about water? And of course, with water, we also need an acid catalyst. You can also write just H3O plus, just combine the 2, that's fine, same thing. So I would expect already that you can draw the 2 products that are possible. Ugh. one of them, geez. One of them would look like this. We'll put the OH on that carbon. Remember, when you're adding water across the double bond, then one of the carbons gets the OH and the other gets the hydrogen. And you can write the bond of the hydrogen here. It's not wrong. But equally, if you don't draw it, it's understood. This carbon is now a CH2. One of those hydrogens was there to begin with on the alkene, and the other one just got put there. So that's one of the products. What is the other possible product? The other possible product has the OH and the other carbon, or rather, we could say the OH and the hydrogen are switched. So the OH now is over here. So those are the two possibilities. And the truth is, by the way, you actually will get both. You'll get a little bit of the other product, most likely. But I think overwhelmingly, the major product, and you'll know what to do because the question will say it. It will ask you for the major product. Sometimes OWL may ask you for both products. You know, the way you know what to put is by what the question is asking you to do. So you have to read the directions. But ordinarily, as organic chemists, we're interested in the major product. And we hope that the major product is the one that we want, right? If we're trying to make a new drug molecule or something, it'd be really bad if 97% of the reaction mixture is some crap we don't need, right? So ordinarily, we try to work things out so that the major product at each step is tending towards the compound that we want. That's just sort of strategy for organic synthesis. But be that as it may, couple things before I go on. Can you all see that in both cases, I've taken the formerly alkene carbons and turned the double bond into a single bond? I'm following the exact same step-by-step method I gave you the other day. And on one of the carbons, I'm putting an OH, and the other, I'm putting an H. Can you see how I've done that in both cases? And the reason I knew to do that is because I see my reagent is H2O with an acid catalyst, or H3O+. And with the reagent being H2O, surely we know the structure of water, the only possible bond you can break is one of the oxygen-hydrogen bonds. So one part is the hydrogen, the other part is the OH. Make sense? So OH could go with the carbon at either end of the double bond when it turns single. In principle, yes, that's true. Good question in chat. But our issue now is which of those is the major product. And that's normally what we care about. The major product is going to be the one that we'll get the most of. In real life, ordinarily, you will get some of the other product. And by the way, I won't give it away. I'll go through Markovnikov's rule once with you. But in this particular case, I would be shocked if you got more than 2 or 3% of the other one. I think the vast majority of the product will be the one that we predict by Markovnikov's rule. So you can count on Markovnikov's rule. So here's how you do it. What you do is you look at your two structures and you compare them to the starting material. And what you make up your mind that you're going to do, again, this is all in the class notes. I've defined everything there. It's in the section of the class notes on 3.8. What you will notice is that of the two alkene carbons, one of them will have more hydrogens directly attached than the other. This carbon here has 0 hydrogens directly attached. So the ones in the CH3 don't count. I'm talking H is directly attached to that alkene carbon. For that one, it would be 0. For this one, it is 1 hydrogen directly attached. So that's a determination you will always be able to make. On any exam question that I would consider fair, this is a determination that you always will be able to make. I'm not interested in asking trick questions. Sometimes I do on accident, but it's not something that I aim to do. So on the exam, you will always be able to make the determination if you need to, as to which carbon is more H's directly attached. So I think you'll agree this carbon is 1 H, that is 0 H's, this one is more H's directly attached. So far, so good? Okay, and then Markovnikov's rule says, of the two pieces, in this case it's H and OH, it could also have been H and Cl, H and Br, H and I, or H and sulfate. Those, I think, are the only 4 we're doing of adding unsymmetrical reagents. So then you look at your reagent and you observe that you've got the H and you've got the other piece. And Markovnikov's rule says, having made this determination, you put the H on the carbon that has more H's directly attached, which again, you will always be able to make that determination. And you put the other piece on the carbon that has fewer hydrogens directly attached in the starting material. That's how you know. Always, no exceptions, you can count on it. You will always be able to make these determinations. I'm not interested in trick questions. Like I said, sometimes I make them anyway. It's called screwing up. We all do it, we're human. But it's not something I aim for. My goal will be that you will always be able to make these two determinations and come to the conclusion of which is the major product. So we conclude that this one is the major product. And while we probably wouldn't get too much of it, this we probably would get some, but only a very minor amount. You'll know what to put based on how the question's phrased. But that's the situation for this reaction. And like I said, I anticipate you would get at least 98% of this one. The amount that you get of this will be negligible. Can I say that one more time? I doubt it, but I'll try. But again, what you have to know about Markovnikov's rule and what Markovnikov's rule is in the class notes. It's in section 3.8. But I'll try to say it one more time. What I think I said, you can correct me if I'm wrong, is that you first figure out which of the two alkene carbons has more hydrogens directly attached. And again, you will always be able to make that determination. I'm not out to try to trick you. Then you'll look at your reagent, and I think you'll find it's going to have an H on one side and something else on the other. And so Markovnikov's rule says, of those two pieces in the reagent, the H goes on the carbon with more H's directly attached, and the other piece goes in the carbon with fewer H's directly attached. One more time, the H goes on the carbon with more H's directly attached, and the other piece goes on the carbon with fewer H's directly attached. That gives you the major product. The other one might be formed as a minor product, but in most cases it's pretty negligible, a few percent at most. Sometimes it's too little even to detect. So we'll do some more examples, don't worry. And like I said, if you missed it, you can A, watch the YouTube video, or B, it's all in the class notes. I've even given you a step-by-step method to apply Markovnikov's rule. Now, I will have you know, this is not the fully theoretically explanatory version of Markovnikov's rule. This is why I'm hoping I have at least a couple minutes to go over one of these reaction mechanisms. I won't spend a lot of time on it. It's not something I'm going to put on any exam heavily, maybe a little bit, but not heavily. But the thing is that it explains the whole thing, because there's no, little wizard with, molecule-sized wizard waving his Harry Potter magic wand around saying H goes here, other thing goes there. It's not like that. There's a very good reason for it. And we understand it completely based on the mechanism. So I think if I take you through it, it is in your book also, but I think if I take you through it, you'll see that it actually explains it. And boy, if you can explain something, it's so much better than having to memorize it, even if the thing is something you won't have to know for your job. I think it's worth learning how to actually understand and master something. I've said that since the beginning. And that's something that we all need to do as adults. So let me do another one. What do you like? Maybe I'll keep this one pretty simple. Let's take just propene, CH3, CH double bond, CH2, and we'll treat this guy with HCl. Let's be interesting, let's make it HI, just to make it a little different. And we have two choices. We could get 2-iodopropane, and we could also get 1-iodopropane, but those are the only two options. Right, and you see how I did that. I looked where my double bond carbons were, I turned it into a single bond, and on one end I put the H, and the other one I put the iodine. And those are the only, that's a lone pair, though you'd be hard pressed to tell. Kind of looks like a person. There we go. So you put the H in one carbon and the iodine in the other. You just look at what you're given and figure out what your two pieces are. I think you'll find it's always an H and then the rest of it, whatever that might be. Does everyone see what I mean when I say an H and then the rest of it is the other piece? That's something you're going to have to be able to do in your own. Good. So I think you'll agree these are the only possibilities, 1 iodopropane and 2 iodopropane. Markovnikov's rule says we'll put the H where there are more H's. Well, this is a CH2, there's 2 H's directly attached. This one just has 1 hydrogen directly attached. So Markovnikov's rule says, in short, it's a carbon over here, that the H will go onto this carbon and the iodine on this carbon in preference. So I think that's going to be the major product. Sorry about my writing. This will be the minor product. And again, you'll know what you have to write down based on what the question says to do. Your exam will be multiple choice, so that limits the options of what you have to put down. Basically, you'll put down A, B, C, D, or E, something like that. But as I said, there's a good reason for all this. That's because the mechanism of this reaction is known, and it's not that complicated. It's only 2 steps. Some mechanisms have 10 steps, and in 227 and 228, we learn ones like that. This one is only 2 steps. And this has all been determined experimentally. This reaction mechanism has been known probably for close to 100 years, certainly at least 50. And so using this compound as an example, let me take you through the mechanism. This is where we use curved arrows. And this, by the way, is the non-bogus way to use curved arrows. This is what curved arrows were meant for, is showing the movement of electrons in a reaction mechanism. So the first step of the reaction mechanism involves breaking that hydrogen-iodine bond. It'd be the same if it were sulfuric acid. It'd be the same if it were HCl or HBr. It even would be the same with adding water, except instead of iodine here, you'd have OH2. In other words, this would be an H3O plus ion. So the mechanism is in fact the same for all of them. The only thing that differs is the identity of the non-hydrogen piece, so to speak. But in the first step, that's a 2, by the way. In the first step, we're going to break the carbon-carbon double bond, which we already know is going to happen because we don't see a double bond in the product. So nothing mysterious here. And we're going to form a new bond between this carbon and the hydrogen, which we already know is going to happen. And so the way we do that is we're going to draw 2 arrows. We're going to draw one arrow that goes from that double bond towards the hydrogen. This shows that this bond is breaking, but remaining attached, if you will, to this carbon. It's kind of swinging out like this, and then it grabs H plus off of HI. No surprise. I think I could do better than that. I mean, you can do kind of like that. You can show the arrow going in between the carbon and the hydrogen, but it might be a little clearer showing it like this. You guys might like that better. That's also correct. So we're pointing it at the H to show that the electrons in that pi bond are going to come out and form a new bond between carbon and hydrogen. Now we can't stop there because as things stand, there's now 2 bonds to hydrogen. That's no good. So we need also to break the bond between hydrogen and iodine, or hydrogen and whatever that other piece is. And that's not so strange. Iodine is a halogen. Halogens are fairly electronegative. So what are you going to get out of this? You're going to get a rather peculiar looking species, but it is a thing that exists. And this is now going to be CH2H, if you will, or CH3, right? Because of those 3 hydrogens, 2 were there to begin with, 1 we just added. This type of intermediate is known as a carbocation, which is exactly what it sounds like. It's a species with a positively charged carbon atom. So it is only 3 bonds around it and no lone pairs. And if you work it out, the formal charge in carbons of that type is +1. And carbocation intermediates are known to exist in this reaction, and in a bunch of other reactions, by the way, including a whole slew of reactions that occur in biological systems. So is it supposed to be an I on top? No, this is still supposed to be a hydrogen, but of course the iodine is still there, but it's not just iodine. Now it's an iodide ion, I-. So that's the other piece that you were thinking of. That's still there. And how do I know that it's I-? Well, because I'm taking the 2 electrons in the hydrogen-iodine bond, and I'm putting them onto the iodine. And there already were 2, 4, 6 electrons there. Now we just added 2 more. So there's 8 electrons around. So since there's 8 rather than 7, that's going to be an iodide ion, not an iodine atom. No, it's a good question. So that's still there. And I bet you can almost guess what's going to happen next. Here you have something that's missing an electron pair. Here you have something with extra electron density. Wouldn't it make the most sense for the thing with the extra electron pair to donate it towards the thing that needs the electron pair? Very logical. And you just draw one arrow to show that. And from that, you get your 2-iodopropane. And that's it, we're done. There, that didn't hurt that badly, did it? Chad is being very polite. So that's the mechanism showing how we get to the major product. So how does that give us information about why we don't get the minor product? Well, we can draw that out too, assuming I have enough room. It's going to be close. Let me see. I think I can select. There it is. Let's try. I think I'll do better with the eraser. I'm going to clear some space above over here because I want to leave that reaction over there. It hurt. Oh, come on. Come on. Like I said, that's a relatively straightforward mechanism. And like I said also, I'm not going to emphasize this very heavily. But here I think it will do us some good. So let's look at the other possibility. How then would we get the other molecule? Because you will get some. It does happen. So let's draw out our propene again. And I could do this with line angle drawings too. I just wanted to make sure I'm being very clear. So now let's put our HI molecule on this side. And now what we're going to do is swing our bond out the other way so that the electrons, if you will remain attached to this carbon and form a new bond between that carbon and the hydrogen. And we're going to take an electron pair away from that guy. And just like before, we'd better break the hydrogen-iodine bond. So we'll show those electrons going round and about the vicinity of the iodine atom. That's the best, I think. And we will once again get a carbocation, but a different one. This is now a CH2. Whoa, that's a long bond. Holy cow. That's now a CH2. I probably will write it as CH2 in the next structure. But now, it's this carbon that has only 3 bonds and a plus charge. And again, one could imagine the iodide ion doing the exact same thing, which it surely would in such a case. It will donate its electrons. Oh, by the way, for some reason in organic chemistry parlance, we say that the iodide ion attacks the carbocation. I do not know why. That term pre-existed me. They were already using it in the 50s and 60s before I was born. So I had nothing to do with it, but it's quite violent. Anyway, after that, you get 1-iodopropane, CH3, then CH2 over here, then another CH2, iodine. And that corresponds to the minor product. So the difference between these two mechanisms is the intermediate. That the way the mechanism goes is the same in both. But in this case, you've got the plus charge on a carbon with 2 methyls and 1 H. So I'm going to put 1 H directly attached over here. This one has just 1 carbon and 2 H's directly attached. And that right there is the problem. It turns out that other things being equal, between any 2 of these carbocation intermediates, the more stable one is the one with fewer H's directly attached. And the more stable, wait, did I say that right? The more stable one has fewer H's directly attached to the carbon with a plus charge on it. The other one has more H's directly attached to the carbon with the plus charge. That's a less stable carbocation. And I think it makes sense why. You've got a carbon atom with a plus charge on here. Sitting around that carbon, we do have one H, but we also have a CH3 group, which is all those electrons and all those CH bonds, and the same thing on the other side. Over here, we've only got the CH2 and 2 hydrogens directly attached. So there's a lot more electron density here. There's a lot more minus charge here to help stabilize that plus charge than on this one. So that's why, so I would say the true statement, sounds like I'm talking about a video game and the true ending, but the true statement of Markovnikov's rule is the major product will be the one that goes through the more stable of all, or the most stable of all possible carbocations. It gives you the same answer. And like I said, I don't want to emphasize this really greatly. Probably I've already spent more time on it than I really wanted to. But I think there's something here that we can understand and that makes sense. Like I said, I'm not going to emphasize this. There's not going to be 20 questions on this in the exam. There could be 1 or at most 2. And we won't do mechanisms very much in the future, maybe once in a while. But my point is they have explanatory power. They help us understand what's going on in the invisible world of molecules. So the reason that we know things is not because we've memorized rules or sentences. We seek to explain them as much as possible. Let's see. So the one on the bottom is more stable than the one on the top. Yep, remember this one was the major product, just like we set up here, and this one's the minor product. And by going through the mechanism, which painful as it was, that's one of the least painful mechanisms I could have given you. But the mechanisms show why that's the case. So I think I've said enough here. I only wanted to tell you enough so that when you read it in your book, you can understand what they're talking about. But there's some real explanatory power here. This is where we can make sense out of science and actually understand why we see what we do when we do these reactions. With that, I think I've said enough about that. That leaves me about 15 minutes to do a very quick review of at least of equilibrium and reaction rates and maybe some basic ideas about reaction energy diagrams, all of which you had in Gen Chem, but 10 minutes on that will not hurt anyone. Good. Everyone okay with that? With leaving it at that? Any questions so far? This carbocation is more stable. It leads to the major product. It always will lead to the major product. Always, no exceptions. And the less stable carbocation always will lead to the minor product. I didn't see who asked that. Does that answer your question? Good. Other questions then? Yes, we are going to do I just have one question for you guys today, provided I can find it. So you'll get 8 points eventually from just attendance. Good. So is this working? This actually relates. You have questions like this on OWL actually. So the question is, we take this alkene that I've called S, and we treat it with HCl. Remember the rules, turn the double bond into a single bond, put an H on one carbon and a Cl on the other, since that's what you're given. And now we even know we'd better put the chlorine on the more substituted carbon, the one that has fewer H's directly attached. So not surprising that that is the major product here. The question is asking you to find a structure of a different alkene that also gives that same product with HCl. And you have questions like this on OWL, so I think this practice is good. So again, I'll say you're looking for a different alkene from this. I haven't started it yet. That's why it's not showing up. Here, let's do this. So there, now you guys should see it. Oh, wait, no, I have to start it, I guess. There we go. Now that I've started it, you should see it. So the question is asking you, boy, people are quick. You're looking for an alkene that's different from this, that if you treat it with HCl also will give you the same compound. Can those of you in chat see the question now? Oh, good, good, good. So we'll take a couple of minutes. Wow, you guys are fast. So you're looking for a different alkene from that when you make the double bond a single bond, put an H on one and a Cl on the other, and even follow Markovnikov's rule, you get the same thing. That's basically what it's asking. I want to go out to at least 2 minutes, let's say. So while we're waiting for the last 45 seconds, I probably should have stressed that. Those of you who are looking for a list of what you have to know for the exam and going through the topics for the exam one by one, I've given it to you already. I've given you a study guide and it's on eCampus. It also has practice questions from last term, the ill-fated spring 2020 term. Although wave to the camera, yeah, anyone's guess if this semester is going to be worse. I hope not. We want the, well, you know, they want the answer key too. Well, you know, this is already a waste of time and paper. What I really just need to do is sort of go into my grade book and give everyone A's. That's the quickest way, you know. Anyway, how is the exam going to work on Monday? God willing, when the creek don't rise, it will appear on eCampus, and it will open at, when will it open? Maybe a little bit before 2:55, because like I said, in case there are internet disasters, I want to make sure that everyone has a chance to go back and start over if they have to. And it's all pretty self-explanatory. Start a petition? No, no. I am required to write an exam. Jeez. Okay, last chance for answers. One question, yes or no exam. That could be pretty bad, actually. Okay, so we're looking for an alkene that's different from this that will give you the same product. Well, D is the same as S. All I've done is flipped that over. So that's not a different compound. I think you'll agree, well, C is just nuts, like the methyl moved over. When you look at B and E, if you put H's and Cl's here, whichever way you do it, it's going to be a different compound. So I think the only one left is A. And in fact, A would give the same major product if you treated it with HCl. The Cl would go in the more substituted carbon, the one with fewer H's directly attached, the H on the carbon with more H's directly attached. So I think the best answer is A. Let's see what you guys thought. Good, that was the major answer. Lockdown browser, no. I've heard very bad things about the lockdown browser. Zoom, yes. Yeah, Zoom, yes. It is going to be proctored, and it will all be recorded. Yeah, I've heard first of all that the lockdown browser always crashes, and even when it doesn't even do what's required of it. So it sounds like a bad deal to me all around. I've heard really disastrous things about the lockdown browser. Good, but I'll have more information on, oh, and it messed up your computer too, great, that's awesome. I'll have more information, I'm sure, by Friday, and probably in at least one email. Log into class in Zoom, and then it'll be something like that. I might make it so that I might up the security on logging in. You might need, I think it will be the same Zoom number. Obviously, if it's not, I'll give you the number. But I might have it so that you have to use your UIN to enter it, or how many questions do you have? No idea, haven't written it yet. But I'm gonna write it for 55 minutes with, like I said, some extra time in case people need to start over. But I'll have hopefully more information by Friday. By Friday, I'll have given my first exam in 227, which is gonna be interesting, since it's partly online and partly in person. Good. So let's see. One thing that's reviewed in this chapter is equilibrium. We've actually already reviewed reaction equilibrium a little bit. Oh no, that was the other class when we did acids and bases. So, but just a reminder about how equilibrium works. If you've got some generalized equation, you probably did these till they were coming out of your ears. Well, then the form of the equilibrium constant is product concentrations over reactant concentrations. So your equilibrium constant, K or KEQ, is nothing other than concentration of C. Oh, wait a minute, we need coefficients, don't we? I'm not even looking at chat now, I'm just getting scared. So the coefficients show up as powers, so you raise the concentration to that power, and you did this till you were blue in the face, plugging in numbers. You know, our days of doing all that kind of thing are over. But I just wanted to remind you that this is a thing that exists, basically. And it makes sense, by the way, because if the equilibrium lies more towards the left side, well, then you're going to have more of these guys, and the numerator of the fraction will be larger. So there's no hugely complicated math here. It's not a big deal. But mostly I just wanted to remind you guys that this exists. A completely different idea is the idea of energy diagrams. So, and again, there's some review of that in your book that I would recommend you look over. Remember that in a typical energy diagram, we might draw a few of these sometime. You should have some form of energy on the vertical axis. Could say energy, it could say delta E, it could say delta H, it could say delta G, some form of energy, and that's going to be increasing on the vertical axis. On the horizontal axis, you have what's generally called reaction coordinate. And what that means is as we move further and further to the right on the horizontal axis, the reaction goes more and more to completion. So at the far left, you're just at starting materials, and as you go further and further, you get closer and closer to the products. So you know a typical energy diagram with just one step might look something like this. You'll want to refresh your memory that we call reactions of this type exergonic because the product is more stable than the starting materials. Endergonic reactions also are a thing that would start higher than it ends. So you can tell that by looking at the energy diagram. I don't think we're going to need very much here, if any, that's quantitative. But it would be good for you to refresh your memory on reaction energy diagrams. We're occasionally going to use them. Good. So, but this is the way they're usually set up. Oh, one last quick thing on energy diagrams. And then I have just one short comment about rate, reaction rate, and then we are done. If you're having trouble conceptualizing reaction coordinate, it's kind of the same thing as time. You can say that time is moving forward in that direction. It's pretty much the same thing. You'll get pretty much the same answer. So great, you just had equilibrium in 1 minute, energy diagrams in 1 minute. Now let's do reaction rate in 1 minute. And there is one really important thing that I need to set down here about rate. And that is that reaction rate has nothing to do with the energy change in a reaction. In other words, just as you can't tell by looking at a balanced equation whether the equation is endergonic or exergonic, you can't tell that just by looking at the balanced equation, which means you won't have to because it can't be done. So that's impossible without more data. You also can't tell just by looking at a balanced equation whether the reaction's fast, slow, or anything in between. And one, well, I thought we were only going to have one question. We're already up to question 9. Geez. Anyway, so be that as it may, one example, and I think it's kind of an interesting example that I like to give, is the reaction. You're probably aware that diamond is an allotrope of carbon. And there is a reaction by which diamond converts to graphite, which is the lowest energy, the most stable allotrope of carbon. Let me move that out of the way so I can write graphite. But this reaction is a thing, it's been studied. And as it turns out, this reaction is exergonic. So delta G is negative for this reaction, meaning that the products are more stable than the reactants. What that means is that diamond very slowly turns into graphite. And those of you who are wearing diamond earrings, diamond jewelry, whatever, it's true. As we speak, your diamond is slowly turning into graphite, but you don't need to worry. Although this reaction is exergonic, it does proceed forward with time. The rate is so agonizingly slow. I think the half-life is in the order of hundreds of thousands of years. We will all be long gone before there's any detectable amount of graphite in your diamond. But still, the reaction is exergonic. So my point here is that even knowing that a reaction is spontaneous tells you nothing about how fast or slow it is. And with that, I'm more than out of time. But I've left you some ideas of things to review on those sections of Chapter 3. We'll see on Friday if I want to make a few more comments in Chapter 3, but otherwise we'll start Chapter 4. Chapter 4 is not on Monday's exam. Chapter 4 is on exam number 2. I will still expect you all to come since it's the only time I'm lecturing on it. Other than that, have a great day, and watch your email because I'm sure I'll have more information as time goes forward.